Hello everyone, myself Shalini, working as Assistant Professor in the Department of CSC from Marri Laxman Reddy Institute of Technology and Management. Today I am going to discuss about the topic equivalence relations from the subject discrete mathematics. In the previous session, I have discussed about what is a relation and different types of relations. So, a relation is nothing but a set of ordered pairs that have been derived from set of numbers. So, generally Cartesian product defines the all possible set of ordered pairs on a given set, but relation is formed based on certain criteria. So that is how a relation will be formed, and we have seen different types of relations like reflexive relation, symmetric relation, antisymmetric relation, transitive relations. So let us see what is an equivalence relation in today's session. So equivalence relation, a relation can be said as an equivalence relation only if it satisfies the three properties of the relations. That is, a relation should be reflexive, it should be symmetric, and it should be transitive. So let us recall all the three properties once again. So reflexive. So when you can call a relation as reflexive, suppose if A is defined on set of numbers like 1, 2, 3, and R is a relation where it forms set of ordered pairs with 1 comma 1, 2 comma 2, 3 comma 3, then you can call this particular relation is reflexive. So let us see the definition of this. For every element A in the given set, the relation must hold between A and itself. That is, the ordered pair is formed between the element itself. So here you can see 1 is related to itself 1 comma 1, 2 is related to itself 2 comma 2, similarly 3 is related to itself. So that is, for every element that belongs to the given set capital A, the ordered pair should be in the form of A comma A, where this ordered pair belongs to the given relation, then only that is known as a reflexive relation or a reflexive property. So next, let us go for the next property, that is symmetric. So what is a symmetric relation? So here let us take an element A. It is related to an element B. So what does it mean? A related to B in the sense the ordered pair in the form of A comma B. Then B must also have to be related to A. That is, there should be an ordered pair in the form of B comma A. Then only you can call that relation as symmetric relation. So here you can see, for all the elements A comma B that belongs to the given set capital A, if you have an ordered pair A comma B that belongs to R, then you must also have an ordered pair B comma A that belongs to R. So let us take an example again. A equal to set of 1, 2, 3, 4, and R is a relation defined as 1 comma 1, 1 comma 2, 1 comma 3, 2 comma 1, and 3 comma 1. So let us verify whether this is a symmetric relation or not. So first one, you are having 1 comma 1. So for 1 comma 1, the symmetric is again 1 comma 1 only, because here 1 is A and the other one is B. For A comma B, B comma A is again 1 comma 1. So it satisfies symmetric relation also. And coming to the next element, that is 1 comma 2, there exists 2 comma 1. For 1 comma 3, there exists 3 comma 1. So we can say that the relation is going to follow symmetric property. Okay. And coming to next one is transitive. So when do you call a relation as transitive? So let us consider that an element A is related to B and B is related to C, then there must be an element that is A related to C. So here you can see all the three elements A, B, C belongs to the given set A. If you have the relation in the form of A comma B belongs to the relation R and B comma C belongs to the relation R, then there must exist A comma C that belongs to R. So here let us consider an example again. Let us take the set of elements 1, 2, 3. So here if R is a relation defined as R equal to 1 comma 1, 1 comma 2, 2 comma 1, 1 comma 3, 2 comma 2, 2 comma 3. Now see here, we are having 1 comma 1. So this is A and this is B. A comma B and this is B comma C. So A comma B, B comma C is there. We should have A comma C also. That is 1 comma 2. So 1 comma 2 is already existing. And let us go for the next 1 comma 2, 2 comma 1. Now in this case, this is A, this is B and this is B, this is C. So 1 comma 2, 2 comma 1, you should have 1 comma 1, 1 comma 1 is existing. And come to the next relation, you are having 2 comma 1 and 1 comma 3. So this is A, this is B, this is B, this is C. So 2 comma 1, 1 comma 3, there should be 2 comma 3, you are having 2 comma 3. Okay. And next, so for 1 comma 3, so there is no element that starts with 3. And next again let us go to 2 comma 2 and 2 comma 3. So this is A comma B and this is B comma C. So for this AB, BC, AC, that is 2 comma 3 is already existing. So you can say that it is following a transitive property. So here one more thing we need to remember. So if there is A comma B and that is A comma B belongs to R, then B comma C, if it does not belong to R, then we need not verify for A comma C. A comma C also does not belong to R. In this case also you can say that an element follows a transitive relation. So that is generally if A comma B belongs to R, B comma C belongs to R. If both are present, then definitely we need to check for A comma C whether it is present in R or not. Then only you call it as transitive. Similarly, suppose if there is A comma B, let us take this relation and in this relation, let us consider you are having one more element called as 4 and I am having only 3 comma 4 here. So I am having only A comma B. But I don't have any B comma C here. There is no element starting with 4. And so I need not check for A comma C. So only A comma B is there that belongs to the relation. There is no B comma C that belongs to the relation and you need not check for A comma C that belongs to the relation. So this also follows the transitive property. So these are the three relations you need to follow to tell a particular relation is an equivalence relation. First is it should follow reflexive property, next is symmetric property and next one is transitive property. So let us consider an example on a set of numbers. Let us consider set A is having 4 elements 1, 2, 3, 4 and we are defining a relation on this set as follows that where R equal to 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4 and you are having 1 comma 2, 2 comma 1. Now we will verify whether is it an equivalence relation or not. So to verify whether it is an equivalence relation, first you have to verify reflexive property. So check how many elements are there here. 1, 2, 3, 4 elements are there and all the elements are following the reflexive property. That is you have 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4. That is every element is related to itself. So you can confirm that it is going to follow reflexive property. And the next one is symmetric. So here you can check for A comma B 1 comma 1, the symmetric is again 1 comma 1 only. For because 1 comma 1 is A comma B, B comma A is also 1 comma 1. So similarly 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4 are already following the symmetric property. So next we will go for 1 comma 2 where A and B both are different values. For 1 comma 2 there exists 2 comma 1 also. So for A comma B there is B comma A also. So you can consider this as following the symmetric property. And coming to transitive, so transitive you have 1 comma 1 and again the element that starts with 1 is 1 comma 2. So if you consider it as A comma B and this is B comma C, you are having A comma C that is 1 comma 2 is already present. And similarly for 2 comma 2, you are having, if you consider this as A comma B, 2 comma 2, the again check for the ordered pair that starts with 2. So this is B comma C, 2 comma 2, 2 comma 1. You are having 2 comma 1 is also already present. And come to the next element 3 comma 3, you are having only A comma B. There is no B comma A here. So that is it is already following a reflexive property. So it satisfies a transitive also. Similarly 4 comma 4. So here since it follows a transitive also, you can declare this particular relation is an equivalence relation. So that is, it follows reflexive, it follows symmetric, and it follows transitive. So this is about an equivalence relation. And the next concept is equivalence class. So what does a class define? Equivalence class define here. So we have seen that equivalence relation should follow all the three properties in order to say it is an equivalence relation. Similarly, equivalence class is used to divide the set into different disjoint sets. That is, there are no common ordered pairs repeated. We are defining a set into different disjoint equivalence sets. Based on this equivalence relation property, a class of that type is known as equivalence class. So let us hear. Equivalence class is a name that we give to the subset of S. So S contains a set of elements we are considering, and if you take the subset of that particular set in which it includes all the elements are equivalent to each other. So how do you say that the elements are equivalent to each other? Suppose if I am having a set called as set 1, 2, 3, 4, 5, and I am going to form a subset of this, and here I need to tell few elements of this are going to be equivalent. So how can I decide that equivalency between them is, first of all I need to check whether that particular relation follows the equivalence relation property or not, because for a given set of elements the relation will be given, that is set of ordered pairs will be given. So based on the ordered pairs we'll check all the three properties: reflexive, transitive, symmetric. If it follows all the three, we say that is an equivalence relation. And after that, you are going to check for the equivalence class. That is, you are going to divide the original set into different subsets which are following the equivalency here. So how we'll verify that, we'll see. So if there is an equivalence relation between any two elements, then those both elements are called as equivalent. Now that is the definition of equivalence class. You can see, given an equivalence relation on set S, you are going to form an equivalence class with respect to an element. For every element in set, you are going to form the equivalence class. So the equivalence class is represented in this format, that is, for an element X that belongs to the given set capital S, you are going to check what are all the elements that are going to relate with A. That is, if I am going to find the equivalence class of a particular element A, then what are the ordered pairs I need to verify? I need to verify the ordered pairs which are in the form of X comma A. So these elements, what are all the elements present in the place of X? They are equivalent to this particular A. So now let us go for an example. Consider a relation on the set of elements you are having 1, 2, 3, 4, 5, 6, and R is given as the set of ordered pairs. So here this is already following an equivalence relation. You can even verify. So totally you are having 6 elements here, and it is following the reflexive property. That is, you are having 1 comma 1, you have 2 comma 2, 3 comma 3, 4 comma 4, 5 comma 5, and 6 comma 6. And next you can check for symmetric property also, that is, for 1 comma 3 you have 3 comma 1, 1 comma 5 you have 5 comma 1, and 2 comma 6 you have 6 comma 2, 3 comma 5 you are having 5 comma 3. So it is following even symmetric also. Next you can go for transitive. You can check here for 1 comma 1, 1 comma 3 you are having 1 comma 3 already, and next 1 comma 3, 3 comma 1 you are having 1 comma 1, 1 comma 5, 5 comma 1 you are having 1 1, and 1 5, 5 3 you are having 1 3, and similarly 1 5, 5 5 you are having 1 5, and next you can check for 2 2, 2 6 you have 2 2, and next 2 2 you don't have any element starting with 2, go for the next ordered pair 2 6 and 6 2 you are having 2 comma 2, and 2 6 6 6 you have 2 comma 6. Similarly 3 1, 1 1 you are having 3 comma 1, and next 3 1 1 3 you have 3 comma 3. Similarly 3 5 5 3 you have 3 comma 3, and next 3 comma 3, 3 comma 1 you have 3 comma 1, 3 comma 3, 3 comma 5 you have 3 comma 5 again, 4 comma 4 is only one element, you need not check anything here, 5 comma 1, 1 comma 1 you have 5 comma 1, that's all. 5 comma 3 and 3 comma 1 you have 5 1, 5, 3, and next 3, 5, you have 5, 5, and next 5, 3, 3, 3, you have 5, 3 again, and next 5, 5, 5, 3, you have 5, 5. Similarly, 6, 2, and 2, 2, you have 6, 2. 6, 6 is a single element. So you have verified here all the elements are following all the three properties: reflexive, symmetric, and transitive. So you can declare this as an equivalence relation. Now we are going to form equivalence class for all the elements. So as I said, for the given set of elements capital S, you are going to form subsets of the elements. That is, we are forming a disjoint set. That is, no element will be repeated in that equivalence class. So now you can check here. The equivalence class for the elements. Let us take the first element in the given set, that is 1. So as we have discussed, that is, for a particular element you can form equivalence class by collecting all the ordered pairs which are in the form of x comma a. So here x may be any element, but a is the element for which you are finding the equivalence class. So here for 1, now you can check 1 should be in this place, and what are all the elements present in the place of x. Now see here. 1 is related to 1, so you have written 1 here, and next 1 is related by 3, so you have written 3, and next 1 is related to 5, so you have written 5 here. So that's all. So that is the equivalence class of 1. Coming to 2, 2 also. So how we have checked 1 here? The equivalence class of 1 is nothing but ordered pair in the form of x comma 1. Similarly, equivalence class for element 2 will be the ordered pair in the form of x comma 2. So here this is 2, 2 is related to 2, so we have written 2, and this is 2 here, the x value is nothing but 6, so we have 2 comma 6. And coming to the next class, that is 3, you are going to check the ordered pairs in the form of x comma 3. So here 3 is related by 1, so you have written 1, 3 is related by 3, so 3, and 3 is related by 5, so 5, 1, 3, 5. So here you can observe the elements that have been related by 1 and 3 are equal. So you can say that the equivalence class 1 is equivalent to 3. These both are equivalent here. The equivalence class, because the values are same. And coming to the next one, that is 4. So 4 is related by only itself, so we have written 4. And next coming to 5, 5 has been related by 1, 5 is related by 3, and next 5 is related by 5. So 1, 3, 5, which is nothing but it is equivalent to the equivalence class 1 as well as the equivalence class 3. And coming to the next one, 6 is related by 2, and 6 is related by itself 6. So it is equivalent to the equivalency class 2. So this is how you can form the equivalency class for all the elements in the given set. So this is about equivalence relations and equivalence class. Thank you.